let's wait for a couple more minutes and then get started. In the meantime, if you can't hear me clearly or you can't see my screen, please post a message on chat. One more minute and then we'll get started. I think people are still joining. Okay, so welcome to the live session for week 5 in the CS100 course on NPTEL. I'm Prashanti. I'm a PhD student at IISc Bangalore. So let's get started. So I don't know how many of you are attending this for the first time. Hopefully all of you have attended before, but I'll just take a quick pass through this. So we have 3 of these 1-hour live sessions every week by team members, usually at different timings and on different Google Meet links. This would be available on your course announcements page. And the purpose of these sessions is to help you understand the concepts better and also to be able to solve your assignment problems. So we will be taking up problems and questions that are very similar to your assignments, but they will not be the exact same questions as your assignments because you're expected to solve them on your own. And the other thing we will do is also to discuss any doubts from that week's course content that you might have. And I will pause at multiple points during this 1-hour lecture to see if you have doubts. So at any point, if you have a question, either on whatever is being currently discussed or from something from the previous content, feel free to post it on chat. And we will keep audio muted because it becomes a bit chaotic when there are more than 10 people in the room and people randomly unmute. So we will use the chat box for all questions. And post this session, you will get access to both the slides and the recording from the NPTEL announcements page. So hope this is clear. Any questions on the logistics? Okay, let's move forward then. So in week 5, we saw a bunch of topics. So let's just walk through them once. So we continued with threads. We saw things like the benefits of threading. Then we looked at Amdahl's law, which is a scaling concept, right? Which we'll again touch upon today as well. And we looked at different kinds of threads. the user and kernel threads and what possible mappings could be there between them. And then we looked at thread libraries, and we looked at issues with having multiple threads. How do you handle signals? How do you cancel a thread? What happens to the resources that are held by that thread? And then if you fork a thread, what happens to the storage? Do you clone all the memory that is there? Things like that. Then we looked at, and then the major topic that we started was CPU scheduling. So we looked at various criteria for scheduling algorithms, and we also looked at a few algorithms, FCFS, first come first serve, and shortest job first. So all of the questions from your assignment will be based on these topics, and we will also focus on these topics through the questions that are covered today. So let's get started. So here's a simple question to start off. A process can be A, single threaded, B, multi-threaded, C, single threaded or multi-threaded, D, none of the mentioned. So here's how we'll do the questions. So I'll read out the question and the options and prompt for answers. So you can type out whatever you think is the answer on the chat box, and this is not a test, so don't worry about whether it's the right answer or the wrong answer. The main point of making this session interactive is so that I can tailor how I talk about these concepts. So for instance, if people are confused about 2 or 3 options, then I can focus on why a particular thing is the right answer and why the others are not, and that will help you gain a better understanding of your concepts. So don't feel hesitant or shy to post answers on chat. You will not be judged for whatever you post. So with that disclaimer, what do you guys think is the answer for question 1? Any thoughts? Okay, C, single threaded or multi-threaded. C again. Any other answers? Anybody who disagrees with C? Okay, everyone thinks it's C. Let's move forward then. Let's see what's the answer. So the answer is C, single threaded or multi-threaded. And let's take a quick recap of single and multi-threaded processes at this point. So with a single threaded process, meaning a process with one single thread, you see this sort of a view, right? It has its own code, data, files, register and stack. Whereas when you look at a process with multiple threads, you see that the code, data and files are shared across all of these threads, but each thread has its own registers and stack. So this is mainly the difference in layout in terms of a single and multi-threaded process. And you also looked at why do you do multi-threading, right? For instance, you might be able to share resources, and this enables better communication. Then economy is basically that creating multiple threads is cheaper than creating multiple processes, again because the threads share all of these, so you only need to set up your registers and stack, right? So it's more economical to create multiple threads than multiple processes. Scalability, your multi-threaded process can actually run in parallel on the multiple cores that your processor has. And responsiveness is if one part of the process is blocked, as in one thread goes into the blocked state, the others can still continue to execute, right? So now going back to the question, we see that a process can be single threaded or multi-threaded. So I'll pause for a minute here so that people who just joined can take a look at the question and others can ask me if they have any doubts. Any doubts on this? I think it's a fairly easy question. If not, let's move ahead. Okay, so this is something that you might have to work out. So I'll pause a little longer. So according to Amdahl's law, if the program is 100% serial with infinite number of cores, what would be the speed up? A is 1, B is 0, 1.3 and 1.4. I'll pause a little longer here so that if you need to take a pen and paper and work this out, please do so. And when you have an answer, post it on chat. Okay, A1, great. Any other answers? Anyone who agrees with A? B, 0, okay. Anyone else? I'll wait 30 more seconds. Okay, A, which is 1. Anybody else? Okay, I think there are no other answers, so let's look at the answer. So the answer is 1. So let's look at how this is, right? So first, let's go back to what is Amdahl's law and then look at this problem. So Amdahl's law is telling you what is the performance boost that you get from adding additional cores to solve a problem, right? And typically every application has both serial and parallel components. So for instance, think about a matrix multiplication, right? So let's say the multiplication itself can be parallelized. So that's the parallel component of your program. But say there is something before that multiplication that is inherently serial, meaning that it has to execute one after the other and so on, right? Now, if you add additional cores to solve this problem, what is the performance benefit that you get, which is usually measured in speed up. So in a lot of parallel algorithms and parallel programming, you will hear the term speed up. So let's first talk about what is speed up, right? So speed up is the benefit you get from a parallel algorithm or from parallelizing the problem as compared to the sequential version of the problem. So if you, let's say your sequential version of solving the problem takes 2 seconds, and now you come up with a way to parallelize this task, or you come up with a parallel algorithm to solve this, and that takes 1 second. So what is the speed up that you get? Any answers to this? So the sequential takes 2 seconds and the parallel takes 1 second. What is the speed up that you get? So the speed up is simply 2 by 1. In this case it would be 2. So the sequential divided by the parallel. So you are saying that I am speeding up this sequential task 2x or by 2 times, right? So that is what the speed up measures. Now look at this particular equation. It says something like 1 by s plus 1 minus s by n, right? Let's look at where these terms come from. So for every application, you have some parts that are serial, which is denoted by s, right? Let's think of an application like this. We have some parts that are sequential or serial, which is denoted by S, and the rest is denoted by 1 minus S, which is the parallel part of the program, right? Now, when you parallelize, so in the sequential fashion, when you run this, let's say that it takes one unit of time to run it. Now you are parallelizing this, as in you are adding more cores to execute this problem. But do you get any speed up when you add more cores to solve this sequential part of the problem? No, you don't, because that by definition runs sequentially. So that is going to take the same amount of time that it took earlier, whatever time that is. So another way to do this is to say that so this takes the same amount of time, whereas the parallel portion of the problem, which is 1 minus S, now takes much lesser time, because you can split this work among multiple processors that you've added, multiple cores or processing cores that you've added, which here is n, right? So this 1 minus S will run n times faster, or 1 minus S by n units of time. So this is the time that the parallelized version of the problem takes, and this is the time that the sequential version of the problem takes, right? Now what Amdahl's law tells you is what is the speed up for different values of S and P, right? Now let's take an example where the application is 75% parallel and 25% serial. If you substitute this value of S and 1 minus S into this formula with a value of n equal to 2, you see that there is a speed up of 1.6 times. So what this means is, in an ideal scenario, right, you think that I have added 2 cores, or I have doubled my cores, and I should get a speed up of 2 times. But what do you actually get? 1.6 times. And why is this 1.6? Because the 25% of your application that is serial did not benefit from this parallelization, right? And this is also termed, this is also called the law of diminishing returns. So wherein you feed more resources in the hope that it will solve your problem faster, but the more you add, the benefits that you get from adding those resources actually diminish, or they become less, right? And as n approaches infinity, speed up approaches 1 by S. So as you keep increasing the number of processors, what is actually stopping you from getting that speed up is the serial part of your application. You are bottlenecked by that, and it has a disproportionate effect on performance. So if you had an application where, let's say, 25% was parallel and 75% was serial, then even if you added infinite number of cores, the benefit that you would get would be bounded by this 1 by S, which is 1 by 3 by 4. In that case, would be the benefit that you get would be less than 1.33 times, right? So this is what Amdahl's law tells you. And on the right, you also see the speed up curves for different values of S and P. I think I have a better diagram towards the later part of the class, so hold on till then. Let's not pay attention to this. Now let's go back to this problem. So here we say that the program is 100% serial, which means that S equal to 1 and 1 minus S. Okay, I think this is a 1 minus S is 0. So you have 1 by 1 plus 0 by n, which is 0. So, and as your infinity, as your cores tend to infinity, your speed up is still 1, right? So in essence, if your sequential program took 100 seconds to run, even if you add 100 cores, or you add 1000 cores, or you add as many cores as you imagine, it is still going to take the same 100 seconds to run, essentially because you can't parallelize the serial portion, right? So you don't get a speed up, and your program is going to take the same amount of time. And Amdahl's law is also more popularly referred to as strong scaling. and I think there is a typo in this part of the formula. I will fix that. So let's go by this speed up formula for now. And the interesting thing to note here is that it doesn't say speed up equal to, it says speed up less than equal to, as in this is a theoretical limit on speed up. The practical speed up that you get oftentimes is lesser than this, and it could be lesser than this for a variety of reasons. For instance, caching effects are one of the main things. When you add cores, there might be differences in caches, whether they are shared, whether they are separate, and how much data comes from the cache versus how much data comes from memory. And that's why the speed up might in practice be less than this. But when we talk about theoretical speed ups, we calculate the upper bound, as in the value that this RHS gives, right? So hopefully this is clear by now. Any doubts on this? I'll wait for 30 seconds to see if you have any doubts and then move on to the next question. We'll see a little more about Amdahl's law in the later part also, as I mentioned. Okay, if there are no questions, let's move to the next one. Multi-threading on a multi-CPU machine decreases concurrency, increases concurrency, doesn't affect the concurrency, can increase or decrease the concurrency. What do you guys think is the answer? Any guesses? Okay, B, increases concurrency. Great. Anyone else? B, okay. Okay, let's look at the answer. Yes, it is increases concurrency, and I think this is a fairly straightforward answer, right? I hope you remember the definition of concurrency and also the difference between concurrency and parallelism from last time. So concurrency need not be parallelism, but it could be parallelism, as in concurrency includes parallelism. Concurrency is basically when you take a look at the progress that multiple processes are making, and over that window it looks like all of them are simultaneously making progress, but they are not, or they need not be running in parallel. So if you have a multi CPU machine and you also enable multi-threading, it means that these threads can actually run on different CPUs, right? And that increases concurrency, it also increases parallelism. So hence the answer is B, increases concurrency. Any doubts on this question? Since we are almost at 25 minutes, does anyone have any doubts from this week's course content? If so, feel free to ask it now. If you have doubts from any other week's course content also, please feel free to ask. If I am not able to answer you right now, I'll make sure to put a slide into this deck. No questions? Okay. This is again on multi-threading. Which of the following components of the program state are shared across threads in a multi-threaded process? A. Register values, B. Global variables, C. Heap memory, and D. Both B and C. So which of them is shared? Any guesses? Remember the diagram we discussed right after the first question that actually had this. Okay, 4D, which is both B and C. Another answer saying both B and C. Okay. Anyone who thinks differently? A. Register values. Interesting. Yeah, and the answer is both B and C. So the heap and so yeah, let's look at the question once more. Which of the following are shared? Register, global variables, heap. So registers are not shared, as you can see, they are separate for each thread. And the global variables, which is in the data section, is also shared. Similarly, the heap, although it is not shown here, is also shared between threads. And so the registers and the stack are the only things that are created for each thread separately. So I hope that's clear, and this is also a pretty straightforward question. Let's go to the next question then. This in this week 5 we have some questions that involve numericals and actually taking a pen and paper and solving it, right? So those questions will take a longer amount of time. So I will try to keep the other questions like question 4 a little short. But if you have a doubt, feel free to ask the question and then I will take time to explain it. So let's move on to question 5. So determine the average waiting time for the following set of processes scheduled using first come first serve policy. Assume that the processes arrived in the order P1, P2, P3, P4, P5, and for each of them the burst time is given to you 5, 15, 20, 40 and 5, and so you have to figure out the average waiting time, and the options are 3, 29, 145 and 5. So I'll wait a whole minute or two even for this question because it will take time for you to do it, but please take a pen and paper and actually solve it. Does anyone have an answer, or is anyone still solving it, or are you stuck in understanding the question? Okay, I have one answer saying B 29. Great. Anyone else? If you need more time, I can wait for 30 more seconds. Okay, if there are no other answers, okay, one more answer saying B. Great. Let's take a look at the answer then. So the answer is B 29. So 2 people got it right. Very happy to see that. So let's now look at why that is the case, right? Yeah. So let's first draw this schedule or the Gantt chart for these processes, right? So you have P1, P2, P3, P4, P5, and they are going to be scheduled using the first come first serve policy, meaning that if P1 arrives before P2, P1 will be scheduled before P2, right? So they are going to be scheduled in the order of arrival P1, P2, P3, P4, P5, right? So let's write those 5 along the x-axis and then let's mark the times for each of them. So P1 takes 5 units of time, let's say seconds for simplicity, it could be milliseconds or microseconds even for that matter, but let's say 5 seconds. So P1 takes 5 seconds to run, after which P2 is scheduled, and P2 takes 15 seconds to run. So by the time P2 has finished running, it is going to be 20 seconds according to the wall clock time. And here an important, it's not very important but a very nuanced thing is that there is a small amount of overhead, this gap that I have indicated between the two, which is actually the scheduling time, right? It's not effortless because there is something called a context switch wherein you save the state of P1 and then you bring back start executing P2. That context switch and the scheduling decision takes some amount of time, which is referred to as the scheduling overhead or the context switch overhead, right? But in all of these schedules, we never show that. We just take it to be 0. And that is a fair assumption because things like the context switch and the scheduling decision are supposed to be really lightweight. I think I was talking about this in one of our earlier sessions. So if P1 takes 5 seconds to execute, the scheduler can't take 5 seconds to make a decision. Then it's a really bad scheduler because you're spending as much time on the scheduling as you are on running the workload, which means that your overhead is 100%. One second. Yeah, sorry about that. Which means, yeah, so you can't have a scheduler that is as inefficient as that, and extending that, we make the assumption that the scheduling and context switch overhead is minimal enough to be ignored. So in this case, we are saying that P1 finishes at 5 seconds and P2 starts executing at this very same instant of time, which is practically not possible, but it's a reasonable assumption to make. So with that, let's move on. So P2 takes 15 units of time to execute, which means that it finishes at 20. P3 takes another 20 units of time, which means that it finishes at 40. And then P4 takes another 40 units of time, finishing at 80. And P5 takes 5 units of time, and the whole execution ends at 85. Now the question is, find the average waiting time. means the waiting time across all these processes. So I hope you remember what waiting time is. We will recap that in the next set of slides. But waiting time is basically how much time did a process have to wait before it was picked up for execution. So P2 arrived at, let's say, time 0, very close to 0, but it had to wait 5 seconds before it started to execute, right? And similarly, P3 arrived at 0, but it had to wait 20 seconds before it started to execute, right? And so on. So that's how you calculate the waiting time for each process. So for P1, there is no waiting time because it arrived and it started executing. Whereas for P2, there is a wait time of 5. Okay, so this 5 is the wait time for P2. Similarly, for P3, it has to wait for P1's execution plus P2's execution, which is 5 plus 15. And for P4, it had to wait for all these three. So 5 plus 15 plus 20. And for P5, it had to wait for all four, 5, 15, 20 and 40. And so this is the waiting time for each of these processes. So you add all of this and divide it by 5, which comes out to be 145 by 5. 145 is the sum of waiting times. The average waiting time is 145 by 5, which is 29. And that's your answer here. So any questions on this? It's a bit elaborate, so hope you followed. Any doubts? Okay, why divide by 5? Because it's the average waiting time and not the sum of the waiting times. So see, one question is, what is the waiting time for P4? Then you would say it is 5 plus 15 plus 20. Another question could be, what is the waiting time for all of them put together, right? Then it's 145. But here the question is average waiting time, means that it is across all these processes and you want the average of all the waiting times. So there are 5 processes here. So you take all of their waiting times, you add them up and then you divide it by 5, which is basically averaging, right? So, and that's why it's divided by 5. So if you had 6 processes and you were asked the average waiting time, you would divide the total waiting time by 6. So whatever the number of processes is, and you will divide by that quantity. Is that clear? Great. So let's move to the next question. If the degree of multi-programming is low, then which statement is correct? Turnaround time and CPU utilization will be low, waiting time will be high, turnaround time will be high, none of the above. Any answers? Okay, A, turnaround time and CPU utilization is low. Great. Anyone else who thinks differently? B, waiting time will be high. Okay. Okay, let's look at the answer. So it's A, turnaround time and CPU utilization will be low. So let's start with looking at these definitions to understand what each of them mean. So CPU utilization means how busy the CPU is, right? So the scheduling criteria is that you want to keep the CPU as busy as possible. So remember that one of the goals of the operating system is to utilize the system efficiently, right? And for the CPU, that means keeping it as busy as possible, because if nothing is running on it, then the CPU power or the compute capability is wasted, right? So the operating system, through scheduling, tries to make sure that the CPU is kept busy. Another criteria that you have is throughput, number of processes that complete their execution per time unit. So how fast are processes able to complete their execution? And turnaround time is the amount of time to execute a particular process, whereas waiting time is, like we saw in the previous question, the amount of time for which the process has been waiting in a queue, right, before it even starts execution. Response time is the amount of time it takes from when a request was submitted until the first response is produced. So this first response need not be output, right? It can just be one part of the output or some response that comes back, right? And that is another measure of time, measure that can be used for optimizing scheduling, right? So these are different measures, and you can design a scheduling algorithm that tries to optimize for one or more of these. And that's why we have these different metrics, right? Because there's a lot of work in the scheduling space, right? And some of them try to maximize throughput, some of them try to maximize utilization, some of them might try to minimize turnaround time, waiting time, and response time. And there might be certain trade-offs. Let's say you try to do one thing, let's say you try to increase CPU utilization, and you might end up having a longer waiting time. Such kind of trade-offs are possible. That's why when we take an algorithm, we try to look at all of these metrics and say that, oh, this algorithm is good in terms of this metric, but it is bad in terms of this metric. And that gives you a holistic picture of the algorithm, and it also tells you about which workload that algorithm might be suitable for, right? So this is something that's a very high level concept, but it's good to keep it in mind. Now and degree of multiprogramming, as we saw in the previous lectures, refers to the number of jobs in the system. So if your degree of multiprogramming is low, as in you have very few jobs in the system, then which of these statements would be correct? So the turnaround time and the CPU utilization will be low is the first option. So presumably if you have fewer number of jobs in the system, the CPU can't be utilized as well, because let's say you had 2 jobs, right? So you start executing one, and then let's say this has an IO request, then you move to the other, and you might even have a 4-core system or an 8-core system. If your processes are not enough in number that it can saturate that, then your CPU utilization will be low, right? That's the first part of it. The turnaround time. So the turnaround time is the amount of time to execute a particular process. So if you have very few jobs, then there will be a lesser waiting time, because you can start executing them soon, right? So you have all these queues and multiple processes being present in them. So if you have very few, then because of that your waiting time will be low and the turnaround time will be low, both of these will be low. So that's what makes the option A the right answer. And waiting time will be high, probably not, because you have very few jobs, so you won't have to wait much. So this is as intuitive as imagining a queue, right? So if you have very few people in the queue, and let's say they're trying to use your ATM machine, right? The utilization of the ATM machine, if you measure it over 1 hour, so say once in 15 minutes someone keeps coming and withdrawing some money, the utilization of the ATM machine is going to be low, and the turnaround time, which is the time it takes for you to go and execute your transaction, will also be low. Whereas if you have a long queue, then your wait time will be high, your turnaround time will also be high, and the utilization expectedly will be high. So hope this makes sense. Any questions? So we have 15 minutes to go. So I'll ask again, does anyone have any doubts in the course material for week 5, or even doubts from previous week's content? Please post your questions or doubts on chat. Okay, there are no questions, I guess. Great. Let's move on. Which algorithm is defined in terms of a time quantum? Shortest job scheduling algorithm, round robin scheduling algorithm, priority scheduling algorithm, none of the above. What do you think is the answer? B, round robin scheduling. Great. B. Anyone else? Okay, let's look at the answer. It is round robin. So far I think you guys have looked at 3 algorithms: first come first serve, shortest job first, and round robin scheduling. So first come first serve, literally, as we saw in the previous example, takes whichever process arrived first and schedules it. Shortest job first scheduling, so this one, a caveat to this is it needs to know the execution time of each job, right? If you did not know how much P1, P2, P3, P4 are going to take, then there's no way you would have an idea of which is the shortest job, and therefore which one to schedule first. So that's the caveat to this. But assuming that you know that, you pick the shortest one and you schedule it, and then thereafter the next shortest one, and so on, right? Round robin scheduling is, imagine a kind of what do I say, a circular kind of thing, right? A buffer kind of thing, a circular buffer. So you start from one point, and let's say you have P1 here, and then 2, 3, 4, and then 5, and then it wraps around, right? It wraps around to P1. So now what you do, you start executing them in this order. That's why the term round robin comes from. And how you execute is you give each of them a time share or a time slice, right? How you do this, I think we will see the details in the next week, but this is how round robin works. So you can see that this is what the question refers to as a time quantum, right? The shortest job, and the shortest job basically depends on the execution time, and it picks the shortest job based on that. And here's another option called priority scheduling, which I think you guys didn't see, but as the name indicates, that works on the basis of priority. So you can have multiple tasks, and each of those can have different priorities, and it would pick the one with the highest priority. So round robin, on the other hand, is a very simple algorithm that just gives a certain amount of time or a quantum of time to every process. So that's why the answer to this is round robin algorithm. I think this is fairly straightforward. If you don't have any questions, I'll move to the next one. Great. The interval from the time of submission of a process to the time of completion is termed as waiting time, turnaround time, response time, throughput. So we just looked at these definitions, right? Does anyone remember which of these corresponds to this line above? B, turnaround time. Great. Anyone else? D, throughput. Okay. Anyone else? B. Great. So the answer is B, and I think it was mentioned here. It's the amount of time it takes to execute a particular process. Throughput was the other answer I got, and throughput is the number of processes that complete their execution per unit time. And here's where I think understanding the definition between the difference between latency and throughput would be useful, but I don't have a slide on that, so maybe I'll put that in next week. But for this question, I think it's clear why it's not throughput and why it's turnaround time, because the question referred to the interval from when you submit to when you complete. Whereas throughput is if you take a given unit of time, how many processes complete in that unit of time, right? And they are different, obviously. So the answer to this is turnaround time, and I hope that's clear. I will include slide on throughput versus latency next time, but very briefly, so you might have heard of this maybe in your networking course if you had one. Latency is talked about as how long it takes for one packet to reach its destination, whereas throughput is the number of packets that are processed in a specific amount of time, right? And these are different things, and they have a consequence. That difference has a consequence. So when you talk about how long does something take, you could be talking about latency, you could be talking about throughput, right? So I think adding an example on that will help you guys understand that difference better, but it's not at all related to this question. So let's keep moving. What is the FIFO algorithm? A first executes the job that came in last in the queue, first executes the job that came first in the queue, first executes a job that needs minimal processor, maximal processor needs. Any answers to this? B first executes the job that came first in the queue. Great. Anyone else? B. B. Great. So I think there's consensus on B. So it is first executes, as FIFO stands for, right? First in, first out. So whatever came first, you execute that, and typically that data structure is a queue. So I don't think this needs further explanation. Okay, which of the following is not shared by threads? Program counter, stack, both program counter and stack, none. C, both program counter and stack. C. Great. Anyone else? C. Okay. Again, I think everyone's clear on this, so I won't spend more time on it. I think I have one more question, so I will move to that. So this is again on the Amdahl's law. So if a program has 70% serial code with 5 processors instead of 1, what will be the speed up? So you have 4 options: 1.31, 1.91, 1 and 1.71. So let me know when you have the answer. A 1.31. Anyone else? Okay, let's look at the calculation. So I think, yeah, so if you, I won't work this out since we did a very similar problem in the first part of the question. So you can use the same formula and come up with this. So yeah, you will get 1.31. So because we have 5 minutes and I want to spend it on Amdahl's law and another concept that is known as weak scaling. And again, you will learn more about these things if you take a course on, let's say, parallel programming. And it's in general a good thing to know about scalability, right? So in Amdahl's law, we looked at what happens if you add more cores to a problem where a certain portion of the problem is serial and a certain portion is parallel, right? And here's an example of that, right? And this is something to keep in mind. So you have two parts, A and B, right? The red portion corresponds to A and the blue portion corresponds to B. Now what you do is you make B 5x faster, right? And you see the overall time that it takes for the program. It is this indicates the execution time, right? So this is the time it takes. Whereas let's say you make A 2 times faster, and then you see the time that the program takes, right? It's a lot shorter than this. That's because the A is the dominant part of this program. So going back to Amdahl's law, if the A is your serial part of the program, no matter how much you optimize this blue, as you can see here, the blue part is speeded up by 5 times, and still the impact on your total program runtime is not that much, right? That's what Amdahl's law talks about. And the example below also talks about the same thing. Here you take a case where both of them are equal, right? The serial part is half, the parallel part is half, and you optimize this half 10 times, still your runtime is going to be dominated by this serial part, right? This is what Amdahl's law spoke about. But an important, so basically we learned that the speed up is limited by the sequential bottleneck that you have. But a big assumption that Amdahl's law makes is that your total problem size is fixed as you add these extra processors, right? And that's why you don't have as much of a speed up as you like. Now let's look at a slightly different concept, which is called weak scaling, and this is also known as Gustafson's law, just like Amdahl's law, right? Here the assumption is that you're not only increasing the number of processors, but you're also increasing the size of the problem. So let's say you had a matrix multiplication of 100 cross 100. Now you're adding 10 processors instead of 1. You're also increasing the matrix multiplication itself, the size of that operation, to let's say 1000 cross 1000, right? Then let's see what happens. So here's an example. So this red part is your serial work, and then you have some portion that is parallelizable, right? Now what happens, as you increase the number of processors, the parallelizable fraction of the input work increases, but the serial work remains constant. So this is a characteristic of the problem itself, right? That as you scale up the problem, the serial work does not increase, but the parallel work keeps increasing with the number of processors. Then what you can effectively do is increase, so here P is the number of processors just like we had N. So you see that the parallelizable portion of the work has increased by 4 times, and you add 4 processors to run that completely in parallel. So the total time or the run time remains constant, and this is a very important consequence of this weak scaling, right? So it depends on what kind of a problem you have, and both of these models are very valid. So here you have speed up curves for both Amdahl's law and Gustafson's law, the strong scaling and weak scaling. And you see that in Amdahl's law, so the y-axis is the number of processes and the x-axis is the number of processes and the y-axis is the speed up, right? So here you see that as you keep adding number of processes, your benefits flatten out, your curves saturate, you're now no longer getting a speed up. But the interesting thing here is that you're still getting a speed up, right? And that is because you're not only increasing the number of processors, but the work itself is increasing now. And therefore, your time remains the same and you get this much of a benefit from adding those number of processors, right? So this is termed as weak scaling, and both of these are valid, right? The assumptions that they make are different, and in many tasks or many problems, it's a lot easier to achieve weak scaling, and weak scaling also fits many more problems, right? As you try to increase the number of processors, you're also going to be trying to run more competition. For instance, you might want to, the reason why you increase the number of processes itself might be that you have more work to do, and therefore you do this, right? So in that case, the time would remain constant and you would get a ideal speed up of this much. Like I said, in practice the speed up might be slightly lesser due to other effects, but this is something that's nice to know. It's not strictly part of your syllabus, but since you have strong scaling, it's good to know that there is another kind of scaling called weak scaling, right? Anyway, I think we are at time, so I'll take any questions that you have and hope things were clear. I'll wait for a minute more in case you have any feedback or any comments about the session. Also, please post them on chat. If not, thank you so much for taking out the time to attend this session and hope it was helpful. See you next week. Great. I'll be here for a minute more and then drop off. So yeah, if you have questions, please ask.